from statistical mechanics, one learns that this is an interesting object. So instead of looking at the average of how far I got and divide it by time, I'll look at e to the b dot x time t. So I put this in exponent. And the motivation is that along the paths, these things add up. So as the time increases, if I get here, I get this far. And then from that point, I get that far. So if I put it in exponent, I'm using additivity of trajectories. The idea is you evaluate this for all initial points. And this is now d-dimensional auxiliary parameter. And usually, unless we're really doing thermodynamics, usually we don't know what to make out of these things to really interpret them. In this case, it's something as dimension of inverse length. I will only use it to take derivatives, and then it'll be like z in the famous generating function that you found so unappetizing. Now it's beta, so maybe it's more acceptable if it's a Greek letter. Now, this we can define for any finite time. So this is just space average of all initial conditions where exponential is evaluated at the position where you're at time t. So you can compute it if you want to. But basically this is sum of exponentials, and I usually have the law of motion that the velocity is bounded. So in time t, I don't get further than the maximal velocity time t. So I know that I can bound all these exponentials by something that's e to the t. So as time goes large, I know that this thing will be dominated by exponential behavior. So in time t, it's a sum of things, each one of them, this is, every one of them is smaller than velocity max. So they'll be bounded unless there's something sick about my dynamics. I have singularity. As long as I have sensible dynamics, I'll be summing lots of exponentials, and lots of exponentials, their sum behaves as exponential. I hope you will believe me that that's the way it is. And exponential times something, some number, and that number is very important for us. We have shown that this number is the leading eigenvalue of evolution operator. And this number depends on beta. For example, if I set beta equal to 0, this is average, or 1 equals 1, nothing interesting happens. But if I take beta small or large, it's kind of dual. So for small b, I'll be sensitive to large x. For large b, I'll be sensitive to small x. This thing can be bounded and is expected to behave exponentially. So now what I can do is I can take the derivative with respect to the ith component of both sides of this equation. So when I take derivative here, it'll bring down ith component of x at t weighted by e to the b dot xt. So that's just an identity on the left-hand side. And on the right-hand side, we care about the fastest exponential dependence. So on this side, I'll get the beta I of s of beta. I bring it time down. So now I have a formula that says the first derivative of this leading behavior of the whole sum with respect to I evaluated at beta equals 0 equals limit t goes to infinity. Because when I said beta equal to 0, this is just 1. And this happens to be my definition of the expectation value of the thing. So maybe I can write it here. We have an exact formula that if you're able to compute the rate of the exponential growth of this integral here, of this averaging integral, then the average is exactly that rate divided by bi, ith component, evaluated at beta equals 0. So beta has gone away. And the only thing I care about it is first derivative.